Greetings, sentient beings and gracile hominids. How are we all today? And that is a greeting that makes a little more sense on the basis of what I'll be reading today. Let me briefly explain. The genesis of this stream actually came about a few weeks ago after a chat with my son. We were discussing No Man's Sky, and I commented that it was interesting that all the biochemistry in No Man's Sky appears to be carbon-based, which led to me trying to remember what I could about the potential of silicon instead of carbon in life. And that then led to me looking up the document you can see on the screen. And in fact, I think I mentioned this during one of my No Man's Sky videos. I did make the similar comment. So this is gaming adjacent, if you like, for those who are wondering about No Man's Sky. And if you play No Man's Sky, you may very well end up thinking, why, do they have any silicon-based life forms here? You might think, why aren't there more gas giants? There's all kinds of things you could think about that are science adjacent when playing No Man's Sky, and this is one of them. So the document in question here is On the Potential of Silicon as a Building Block for Life by Janusz Jurand-Pytowski, William Baines, and Sarah Seeger. And they are respectively in the Department of Earth, Atmospheric and Planetary Sciences at the Massachusetts Institute of Technology, the Department of Physics at MIT, and the Department of Aeronautics and Astronautics, also at MIT. This paper was published on the 10th of June 2020 and is only 4 years old. And as I understand it, it kind of reflects an accumulation of all the possibilities for life being based not on carbon, as it is on Earth, but on silicon. But some of this is made plain in the document itself. So, first we'll start with the abstract. Despite more than 100 years of work on organosilicon chemistry, the basis for the plausibility of silicon-based life has never been systematically addressed nor objectively reviewed. We provide a comprehensive assessment of the possibility of silicon-based biochemistry based on a review of what is known and what has been modeled, even including speculative work. We assess whether or not silicon chemistry meets the requirements for chemical diversity and reactivity as compared to carbon. To expand the possibility of plausible silicon biochemistry, we explore silicon's chemical complexity in diverse solvents found in planetary environments, including water, cryosolvents, and sulfuric acid. In no environment is a life based primarily around silicon chemistry a plausible option. We find that in a water-rich environment, silicon's chemical capacity is highly limited due to ubiquitous silica formation. Silicon can likely only be used as a rare and specialized heteroatom. Cryosolvents, for example liquid nitrogen, provide extremely low solubility of all molecules, including organosilicons. Sulfuric acid, surprisingly, appears to be able to support a much larger diversity of organosilicon chemistry than water. In fact, the abstract lays out, as it is supposed to, everything about the document in summary form. So you could stop watching now and simply refer back to the abstract, but where would the fun in that be? Your insomnia might be playing up and you wish to fall asleep. Oops. Introduction. Life in environments very different from Earth's could have a biochemistry that is very distinct from Earth's life. A persistent contender as an alternative elemental basis for life is silicon, mainly due to the chemical analogues between silicon and carbon. The idea that life could be based on silicon rather than carbon was first proposed in 1891 by the German astrophysicist Julius Scheiner. Silicon shares many similarities with carbon and is, in the form of various silicates in rocks, the second most abundant element after oxygen in Earth's crust. However, despite its abundance, terrestrial life only uses silicon as silicic acid and silica. There are no known examples of life using any other form of silicon chemistry. When people speak of silicon-based life, they are usually referring to the diverse organosilicon chemistry, and specifically chemistry in which carbon in organic molecules is replaced by silicon. So why is life's use of silicon so restricted, and could a wider silicon chemistry be used in other biochemistries? The possibility of silicon-based life is usually either accepted as plausible or dismissed out of hand. For example, Carl Sagan famously called himself a carbon chauvinist. However, despite a century of speculation and experimental work on organosilicon chemistry, the plausibility of silicon-based life has never been systematically addressed nor objectively reviewed. This paper seeks to fill this gap. We review what is known, modeled, or speculated about silicon as a basis of life, and provide a comprehensive assessment of the opportunities for silicon in a non-terrestrial biochemistry, with a detailed discussion of the arguments for and against silicon as a building block of biochemistry. We start with the discussion of the general requirements for the chemistry of life, no matter its chemical basis. We next provide the overview of silicon chemistry, including discussion of the diversity of silicon chemistry and thermodynamics of formation of silicon compounds. We then discuss how silicon chemistry meets the requirements for the chemistry of life, focusing on the classes of environments in which life using silicon as a component of biochemistry could occur. We conclude first that in water or ammonia, silicon cannot be the main building block for life, but might be used as a rare heteroatom. Second, that cryosolvents are poor environments for any biochemistry. And third, that in sulfuric acid, silicon could be used much more widely by life. We relegate discussion of the details of how terrestrial life uses silicon to Appendix A, and more detailed background on silicon chemistry and speculation on silicon biochemistry to Appendices B through D. I don't really have any comments. I should point out that my own scientific education only took me up as far as the American equivalent of high school or college here in the UK. And that was more years ago than I care to admit to, like 40. So my memory is a little fuzzy on some details, especially when it comes to interpretation. What I'm going to do is, if I come across something which I find particularly obtuse, I will take the time out to look it up and explain it. However, when I first read this document, I didn't find it particularly difficult to understand, although that may change as I'm reading through it. General requirements for the chemistry of life. We begin by describing the general requirements that any biochemistry must fulfill. The general characteristics that have to be met by any chemical basis for life can be condensed to three essential requirements: sufficient chemical diversity, stability, and reactivity, and the presence of a solvent. Although chemical diversity, reactivity, and solvent requirements are linked, we discuss them separately below. If silicon chemistry is to be a component of any biochemistry, then it must fulfill these requirements. Chemical diversity. Life needs a diverse set of chemicals with different functions. On Earth, the diverse set of chemicals are amino acids to make proteins, sugars and nitrogenous bases to make nucleic acids, hydroxyl and keto acids as core metabolic indeterminates, lipids to make membranes, and more. To build a diverse set of chemical life needs a set of elements capable of building molecules composed of many atoms that will provide sufficient biological functionality. Sufficient chemical diversity needed to build a molecular repertoire suitable for life can only be achieved by a scaffolding element bonded with heteroatom elements. The scaffold atom is one that can join in chains and clusters to construct the skeleton or shape of a molecule, and the heteroatoms provide chemical activity in a molecule. Scaffolds provide the ability to make large molecules, and hence a large number of different molecules. Compare the number of stable molecules of the type XNHM that can be formed with X equals nitrogen, 3NH3, N2H4, N2H2, and with X equals carbon, an essentially infinite number of hydrocarbons. Scaffold elements and heteroatoms tend to be different atoms. The scaffold needs to be relatively stable and unreactive, while at the same time bonding to functional atoms, heteroatoms, that provide chemical functionality and distinctiveness to each molecule. On Earth, carbon forms the major scaffold element, hence the term carbon-based life. Several other non-metal elements could be viable scaffold alternatives to contain carbon in that regard. Sulfur, boron, and in particular silicon are capable of forming covalent compounds in which many atoms of the same type are bound together to form large molecules, and therefore could, in principle, be considered as scaffolding elements. Sulfur-based polymers, e.g. amphiphilic polythionates, are, however, limited to linear chains, which severely restricts the diversity of possible shapes in sulfur-based systems. Boron, on the other hand, forms polymeric structures that are clusters of atoms rather than smaller isolated molecules. For example, decaborane, which while stoichiometrically a boron analog of the hydrocarbon decane, is in structure more similar to a diamond nanoparticle. Among these alternatives, silicon seems to be the most promising choice as a substituent for carbon in biochemistry. Now, what I like about this document so far is they've actually pretty much explained a lot of the terms that they're using or are going to use. I have to wonder whether the authors knew that non-technical people might read this and therefore put it in as simple a fashion as possible. Because the scaffolding of carbon and hydrogen alone provides only the very limited chemical function required for metabolism, heteroatoms are needed to provide chemical reactivity. Heteroatoms can form covalent bonds to carbon or other scaffolding elements, but are more electropositive or electronegative. The difference in electronegativity provides the reactivity of molecules. Heteroatom reactivity is responsible for the great majority of the metabolic reactions occurring in Earth's organisms. Life on Earth uses several heteroatoms, for example oxygen, nitrogen, sulfur, and phosphorus, that form covalent bonds with the carbon scaffold of biomolecules and with each other. Heteroatoms can conveniently be divided into common heteroatoms and rare heteroatoms, although this is for convenience and does not represent any absolute class of abundance, which in any case will vary from organism to organism. Common heteroatoms, for example nitrogen or oxygen in terrestrial life, are used in many different molecules in biochemistry. On Earth, oxygen dominates amongst the heteroatoms used by life. In fact, the oxygen heteroatom is so ubiquitous on Earth, biochemistry has been described as the chemistry of carbonyl groups. By contrast, rare heteroatoms are used in a small number of specific contexts. Examples in terrestrial life include selenium and fluorine. It is plausible that these elements are difficult for life to use widely, but confer specific advantage in the rare molecules in which they are found. For example, the thermodynamics of fluorine make it hard to incorporate into organic molecules, but the toxicity of the resulting molecules makes fluorine valuable in plant defense chemicals. We note that the chemical diversity in small molecules implies a potential chemical diversity in polymers. Proteins are enormously diverse because they can be made from a chemically diverse set of amino acid monomers. I hope that was all clear. Actually, yes, I find that fairly clear. As this is going to be published as suitable for everyone, comments will be open on YouTube, and if you have questions, ask them and I will do my best to answer them. Together, scaffolds and heteroatoms provide the chemical diversity and reactivity required for life. I'm not going to go through all the figures and examples that they are showing here, but they'll be on screen long enough if you wish to, and hopefully in high enough resolution that you can read it for themselves. Chemical stability and reactivity are the second general requirement of the chemistry of life. There must be a balance between biochemical stability and reactivity in their solvent. Biochemicals must be stable to react. Biochemicals must be stable to reaction both with the solvent and with each other over whatever timescale is required for their biological function. Thus, for example, sugars cannot be a component of a biochemistry that uses concentrated sulfuric acid as a solvent, because sugars are dehydrated to amorphous carbon in under a minute in sulfuric acid conditions. However, biochemicals have to be reactive in their solvent to some extent in order to be able to perform their required biological functions. Aprotic solvents, those that cannot donate protons, tend to be less reactive than water, ammonia, and sulfuric acid. Furthermore, reactivity is highly reduced at low temperatures, so almost any chemistry is stable in liquid methane or liquid nitrogen. We would not therefore expect very stable chemicals not to be components of life in cold aprotic solvents, as they would not be reactive enough. Stability and reactivity are therefore a function of the solvent as well as the chemistry itself. We discuss the solvent requirement next. One thing I should point out here is this little section here where it says those that cannot donate protons. That is actually referring to hydrogen. It's not talking about yanking protons out of the nucleus of atoms. This is talking about hydrogen nuclei, or hydrogen ions if you prefer. There are solvents which can donate protons, typically referred to as acids, and there are solvents which can accept protons. Well, they're not technically solvents, but liquids which can accept protons are typically referred to as bases. I think I've got that right. Solvent. Chemical life has to operate in a medium that allows molecules to move, as do liquids and gases, but is dense enough to stop large molecules from simply falling out as aggregates, as are solids and liquids. This means that the chemistry of life has to operate in a dense fluid solution, most plausibly a liquid. Water is widely considered the ideal, possibly the only solvent for life. Water actively assists in the self-organization of membranes and polymers of life, therefore assisting in compartmentalization, a phenomenon that is likely to be a general requirement for life. On Earth, liquid water also plays an active role in life's metabolic processes. I love that paragraph. It beautifully describes why water is so important. Excuse me. Although water is a good solvent for Earth's carbon-based life, many other solvents have been proposed as well suited for alternative biochemistries. For example, sulfuric acid, carbon dioxide, hydrogen cyanide, propane, ammonia, hydrogen sulfide, ethane and methane, nitrogen, and even neon and argon. These liquids broadly fall into the protic solvents. Solvents that, like water, can donate or accept protons from chemicals dissolved in them, such as H2SO4, H2S, and NH3. And aprotic solvents, such as liquid hydrocarbons, or nitrogen. In general, protic solvents are chemically aggressive, and their aggressiveness limits the chemistry that can stably dissolve in them. In contrast to protic solvents, aprotic solvents are generally less reactive and stably dissolve a wider range of chemicals than protic solvents. Solubility of solids in any solvent generally increases with temperature, so cosmically, common aprotic solvents such as liquid methane and nitrogen are poor solvents because they are liquid only at very low temperatures. Thus, the nature and temperature of the solvent in which life operates affects both what scaffolds are viable and what heteroatom chemistry is stable in that solvent. And what that basically means is there has to be a balance. Although I would throw in at this point that it does seem that while chemical reactions are slowed down dramatically when it gets cold, this is a known fact, it does seem that complex carbon compounds can form in the vacuum of space because we have found asteroids with amino acids in them. And either they come from a planet that got blown up and those amino acids had formed on the planet before it was blown up, or they were formed during extremely slow chemical processes as the asteroid was hurtling around space. I'm not sure if there's a consensus. There probably is. I might have to look that up. Overview of silicon chemistry. We start the assessment of silicon as a building block of biochemistry by presenting an overview of the basic physico-chemical properties of silicon chemistry compared to carbon, followed by the discussion of the chemical diversity of silicon chemistry as compared to carbon. We then discuss the thermodynamics of formation of silicon chemicals with a comparison to carbon equivalents, and discuss the thermodynamic barriers in the synthesis of complex silicon molecules. We present new findings on the possible diversity of silicon chemistry based on thermodynamic limitations. Silicon chemistry overview in comparison to carbon. Silicon is the closest analog of carbon. Both silicon and carbon are tetravalent atoms that form primarily covalent, non-ionic compounds. However, there is surprisingly little similarity between them that goes beyond the statement that both elements can form 4 covalent bonds. In this section, we summarize the similarities and differences of silicon and carbon and discuss the consequences of their different reactivities and chemical properties on the formation of complex chemistry. The covalent radius of a silicon atom is larger than that of carbon, which results in generally longer bond lengths and different bond angles. Different bond lengths and angles have especially large effects in ring structures containing silicon atoms, resulting in distinct ring conformations. Right, I got that right. In distinct ring conformations and ring reactivity as compared to their carbon-containing counterparts. The bonding preferences of silicon are also different than carbon, mainly due to the availability of low-lying 3D orbitals that allow silicon to form compounds that have 5 or 6 coordinated silicon atoms. Especially penta-coordinated silicon compounds are readily formed, which allows for many more reaction paths between tetra-coordinate silicon compounds than are available to carbon. Stable penta- and hexa-coordinate silicon compounds are superchiral. Silicon is more electropositive as compared to carbon, nitrogen, oxygen, and hydrogen. The higher electropositivity of silicon creates an electron-deficient center in silicon and results, for example, in a stronger bond polarization as compared to analogous carbon bonds, or in a reverse bond polarization of the carbon-hydrogen and silicon-hydrogen bonds. As a result of those differences, most bonds that silicon forms with nonmetals are more strongly polarized than their carbon counterparts, and thus more susceptible to electrophilic and nucleophilic attack. Even bonds that are considered to be very stable, like silicon-carbon, have higher reactivity as compared to their carbon analogues. For example, silicon tetrachloride, containing silicon-chlorine bonds, is hydrolyzed almost instantly in water, whereas carbon tetrachloride, containing analogous silicon-chlorine bonds, which is also thermodynamically unstable to hydrolysis, is stable for years in the presence of water. Silanes, SiH4, Si2H6, etc., are stable as pure chemicals for many years, but are very sensitive to water in the presence of trace alkali, unlike alkanes. Reactions of both disilane, Si2H6, and ethane, C2H6, with oxygen are clearly exothermic, but ethane may be mixed with oxygen at 200 degrees centigrade without reacting, whereas disilane spontaneously combusts in air at 0 degrees centigrade. We discussed the implications of such differences in reactivity in section 3.2.2, which is lower down. The differences between bond energies for carbon and silicon-containing chemical bonds are also reflected by the disparities in the reactivity of silicon and carbon-containing compounds. The strength of a carbon-carbon bond is a little bit greater than that of a carbon-oxygen bond, while the analogous silicon-oxygen bond is much stronger than the silicon-silicon bond, although the exact bond energy depends on the substituents on the carbon or silicon. As a result of these differences in individual bond strengths, the chemistry of organic carbon molecules is dominated by carbon-carbon polymerization, catenation, the formation of long chains of covalently linked carbon atoms, for example in hydrocarbons. Even though silicon is capable of formation of silicon-silicon catenated structures, for example in silanes, they are much more reactive than their carbon-carbon counterparts, especially in water. As a consequence of the greater reactivity of the silicon-silicon bond, the most common stable polymers of silicon are built from silicon-oxygen chains, as the silicon-oxygen bond is disproportionately stronger than any other silicon-containing bond. Moreover, the polymerization of silicon often leads to a meshwork of silicon-oxygen chains and not linear polymers like for carbon. Recall that the formation of long linear polymers is often cited as an absolute general characteristic of any biochemistry. As a result, silicon chemistry in oxygen-rich environments, for example water, ultimately leads to silica, SiO2, which is a refractory solid rather than a gas, with no double bonds to oxygen, as in its carbon equivalent, which would be carbon dioxide. Diversity of silicon chemistry. In this section, we explore the potential diversity of silicon chemistry from 3 viewpoints: the theoretical diversity of organosilicon chemistry, the observed functional diversity of silicon molecules, and the potential diversity of silicon-based polymers. We conclude with a new assessment that there is, in theory, sufficient potential diversity in silicon chemistry to build biochemistry. And I'm going to skip table 1 because, to be honest with you, I've got no idea how I would narrate that. But I'll leave it up there for a moment so that anybody interested can have a look at it. By the way, on YouTube, I will post a link to where I got this document from. It's in PDF form, so readily downloadable and readily readable. Give me a second, please. Where would I be without my coffee in the morning? Theoretical diversity of silicon chemistry. Silicon can form stable covalent bonds with the same crucial elemental building blocks as carbon. It can covalently bind itself, carbon, nitrogen, oxygen, sulfur, phosphorus, and the halogens, as well as semi-metals like germanium. Silicon can also form covalent bonds with many metals. On top of the versatile binding to many other elements in its most common tetra-coordinate state, silicon can also form stable penta- and hexa-coordinate compounds with crucial biological elements like nitrogen, carbon, or oxygen, with or without overall charge on the molecule. Hey, what? Sorry, did I just... Oh. Moreover, the coordination numbers of silicon are different than that of carbon. Such differences often result in the formation of silicon chemicals that do not have direct carbon analogues, meaning that the potential chemical flexibility of silicon, although achieved through different means, could be as great as that of carbon. There are two types of measure of chemical diversity, structural and functional. Hydrocarbons show a staggering structural diversity, but are chemically monotonous. As noted in section 2.1, there are only 3 stable NMHN compounds, but they show more divergent chemical behavior than all the hydrocarbons. In this section, we address the structural diversity of organosilicons. In the following section, we discuss the functional diversity of silicon. To illustrate the scale of possible structural diversity in organocynical, I hope that's not Freudian. To illustrate the scale of possible structural diversity in organosilicon chemistry as compared to carbon, we generated a set of possible chemical structures that are composed of up to 7 atoms selected from sulfur, phosphorus, oxygen, nitrogen, fluorine, and chlorine as heteroatoms, with as many additional hydrogen atoms as was required to satisfy valence rules, using an algorithm derived from that described in the work of... Okay, that's a reference. I'm not going to go into the footnotes. Again, this is going to be downloadable, so you can look up the... I'll link to where you can load it, so if you want to, you can go through the footnotes yourself. In short, the algorithm takes a set of topological structures defined as alkanes and substitutes heteroatoms into them according to bonding rules. Starting structures and bonding rules are defined to reflect stability and reactivity in different solvents. See Appendix E1 for more details on the calculations of the silicon chemical space. I'm not going to get heavily into mathematics in this. Maths is probably my weakest of all subjects. I think it's even weaker than my knowledge of bovine dentistry. Okay, kidding about that one. We generated sets of structures likely to be stable in water, sulfuric acid, or in a hypothetical aprotic cryosolvent. We did not consider solubility in cryosolvents for the chemical diversity estimation. See section 4.4, which we'll get to in a bit, for discussion of the solubility limitation of cryosolvents, generated with or without silicon atoms. These calculations do not include penta and hexa-coordinate systems, which are underrepresented in small molecules. By definition, there are no 5-atom molecules in which a silicon atom is bonded to 5 other atoms. From our combinatoric study, we find that adding silicon to the repertoire of the chemistry possible in water adds little additional structural chemical diversity. Such a very modest increase in chemical diversity is due to the fact that almost all silicon X bonds, including silicon-silicon bonds, are readily attacked and hydrolyzed in water. In contrast, we find that adding silicon to the repertoire of structures stable in sulfuric acid has a much greater positive impact on the available chemical diversity. In aprotic solvents, where neither attack by H+ or OH- is possible, the increase in chemical diversity is greater still. However, our calculations suggest that overall, silicon does not have a major impact on the structural chemical diversity available to life as compared to carbon. This is because carbon can readily form double and triple bonds with carbon, nitrogen, oxygen, and sulfur, whereas silicon double bonds are strongly disfavored. Although see Appendix C for an overview of exceptions to this generalization about silicon chemistry. Such limitations of carbon chemistry are further exemplified by the efforts to make silicon analogues of terrestrial biochemicals, which have only revealed how different silicon and carbon really are. We discuss the observed functional diversity of silicon chemistry next. We conclude with a few points. First, the vast potential theoretical space of silicon chemistry is almost entirely unstable in water, and hence not available to a biochemistry based on water as a solvent. This major point has been implied from several examples, but never fully emphasized. Second, the presence of silicon adds a greater diversity of molecules, perhaps enough to contribute as a heteroatom component of biochemistry to the available chemistry of hypothetical life based in sulfuric acid. Third, the majority of the chemical space of silicon chemistry is available in aprotic solvents such as dry liquid hydrocarbons or liquid nitrogen. I've got a comment from one of my listeners saying that they hate math. I don't actually hate math, I'm just no good at it. Curiously, my son is very good at math. In fact, he's studying math at A level. I studied math at A level, but I only got a grade E, which can be summarized as I only barely passed. I also did biology and organic chemistry, by the way. And then I went into computer science. Okay, I'm going to skip this page because it's tables which do not lend themselves well to narration. And to be honest, I'm not sure that narrating the figure makes sense without direct reference to the tables, so I will skip that. Oh, I got another comment. Basically, exactly, I hate math because I can't do it. I am actually terrible at playing pinball, but I still love pinball. You don't necessarily have to hate something because you're no good at it. Observed functional diversity of silicon chemistry. The functional diversity of silicon chemistry is demonstrated by the wide range of compounds that have been created in the lab and by their very varied chemical properties, including even some biological uses. We can only provide a brief overview of the diversity of molecules containing silicon, either as a scaffolding element or as a major heteroatom, that are available to silicon chemistry. Such an overview will serve as an illustration of a proof of principle for the chemical diversity of synthetic organosilicon molecules. We discuss several such examples below. Silanes, which are silicon analogues of hydrocarbons, both branched and unbranched, and diverse cyclosilanes, for example, cyclohexasilane, are commonly known silicon analogues of hydrocarbons, polymeric siloxanes, cyclosilane rings with attached OH groups, have no direct carbon analogue but are reminiscent of functionalized graphenes. The linked siloxane ring structures have structural and electronic similarities to the porphyrin units of heme and chlorophyll. Hang on. See Appendix C for the discussion of hypothetical analogous solutions of silicon to the common biological functions. Many complex cage systems, composed of multiple connected ring systems, are also known. One example, and pause while I try and figure out how to pronounce this, is silsesquioxanes, containing silicon-oxygen bond-rich core structures that can be modified with other groups that allow for a precise spatial orientation of the entire molecule, therefore opening the possibility for the complex regulation of the chemical accessibility of the core structure. Mere structural diversity in general is insufficient to support a biochemistry. The chemistry of life must support chemical functional diversity as well. Silicon provides the basis for diverse chemical function when combined with other atoms other than carbon. Several examples include silicon-sulfur bond containing silicon analogues of thiols, that is thiosilanes, and silicon-nitrogen bond containing alpha... Oh, okay, is that alpha-silyl amino acids? I can't remember my Greek lettering system, so I apologize. Hang on. I am just going to check that that is what it is. That is not alpha. Hang on. I'm going to have to look it up now. I'm sorry about this. Oh no, I was correct. That is alpha. Right, now I've got to find out where I was. Here we go. Alpha-silyl amino acids. Dynamic, highly polarized silicon systems where rapid reversible chemistry occurs are also known. Silicon can also provide electron conduction down a silicon-silicon silane chain. Diverse silicon chemicals that have organic carbon scaffolds around the silicon atom, that is, where silicon is acting as a heteroatom, not a scaffold element, are also known, although many react very rapidly with water, which, to be honest, could have been predicted from what they were saying previously, and which is probably why I'm not sure anybody takes seriously the idea of a combination of silicon and carbon in molecules of life, because the silicon bonded to the carbon would react too easily. I think I got that right. Okay, how the heck? Okay. Examples of such chemicals include zwitterionic silicon compounds, a range of organosilicon molecules with negatively charged silicon centers, positively charged silicum, that is tricoordinate silicon, and pentacoordinate silicon, some of which have silicon bonded to 5 different atoms at once, that can have useful catalytic properties in carbon-carbon bond formation. Silicon can form stable structures inaccessible to carbon, such as stable gem diols, which have been shown to be both stable in water and to be pharmacologically promising. Silyl fluorides have also shown specific biological effects, as have other more exotic molecules like hexacoordinate silicon. When silicon is incorporated into an organic compound, the chemical and physical differences contributed by the silyl group can provide such compounds with unique chemical properties, which can lead to subtle biological function different from carbon. These new unique properties lead to useful pharmacological and medicinal applications of organosilicon molecules and open new avenues for unique specific interactions between organosilicon molecules and biological macromolecules. Excuse me a moment. Good examples of such new biologically and pharmacologically relevant properties were shown for silovenlafaxine, where the introduction of silicon into the ring structure provides a conformation that is not accessible with the corresponding carbon analog. One of the persistent myths about silicon chemistry is that it is monotonous, and this is in part because many of the key analogous functional groups in carbon-based chemistry cannot exist in silicon chemistry. Thus, despite decades of effort, no one has succeeded in making a compound with an H and OH group attached to the same silicon atom. Thus, direct silicon analogues of primary alcohols or sugars are impossible. Similarly, silicon doubly bonded to oxygen is not stable under Earth's surface condition, even in the absence of water or molecular oxygen. So silicon analogues of aldehydes, ketones, and carboxylic acids are impossible. However, this is not the point at issue. The question is whether silicon can provide diverse function, and as we argue on the examples presented above, it can. Silicon does so, however, through different chemistry than carbon. We discussed the capability of silicon for complex, diverse chemical functionality on the example of polymer chemistry next. So that could be broadly understood to be, say, basically, you're not going to have a direct analog between carbon-based life and silicon-based life, but because of the the silicon chemistry diversity, you could have replacements for what we see in carbon biochemistry, which is the same thing as saying biochemistry, technically. Apologies for occasional pronunciation stumbles. A long time ago, when I was doing a different YouTube channel, I have fond memories of trying to pronounce the word Schlichting, who, if I recall, was one of the first Germans to be shot down during World War I from another aircraft using a machine gun. That took me several tries before I got it right. Oh, if anybody's interested, that channel still exists. It's called Forgotten Aviation, but for various reasons I no longer maintain it. Observe structural diversity of complex silicon polymer chemistry. Oh, I might one day restart Forgotten Aviation. I'm just saying. Bit of a shameless plug there. If you like early aviation, go visit Forgotten Aviation. Right, where was I? Observe structural diversity of complex silicon polymer chemistry. As a subset of observed silicon chemical diversity, we turn to silicon polymer chemistry. Functional chemical diversity provided by silicon is only useful to life if silicon can form polymers. Virtually every biological process uses polymers. While the specific long polymers used by life on Earth, like proteins, DNA, or RNA, do not have to be universal for all life, it is likely that the utilization of some form of polymers is one of the required general characteristics of all life, no matter its chemical composition. It is therefore prudent to ask if silicon can provide sufficient chemical diversity beyond small molecules as a building block of complex polymers for biochemistry. And actually, there's something I should have said at the beginning of this, in case anybody's wondering. This is an open access document, which my understanding leads me to think that I'm actually perfectly able to read it out like this. If it was not publicly available, I wouldn't be able to do that, even if I had access to the document, but this is publicly available. I don't think this constitutes plagiarism because I'm not attempting to pass this off as my own work. In fact, explicitly at the beginning, I mentioned the authors. So hopefully that is sufficient. Where was I? The capability of silicon polymer chemistry to form sufficiently diverse molecules to support complex biochemistry is often called into question. Silicon chemistry is often called monotonous in comparison to possible carbon equivalents. The myth of the chemical monotony of organosilicon polymers and small molecules likely stems from the comparison of the enormous diversity of carbon-based molecules produced by life on Earth with the known organosilicon polymers used in industry. Clearly, most industrial organosilicon polymers are monotonous, but are also industrial carbon polymers. Oh, sorry, I got that wrong. But so are most industrial carbon polymers, especially those that are not inspired by natural products. Chemical monotony is often required by the intended function of the industrial polymer. Chemical monotony is especially prevalent in plastics, but is not an inherent feature of organosilicon chemistry. There is no inherent chemical reason why diverse high molecular weight silanes or siloxanes could not have a highly diverse and highly structured set of side chains. Basically, comparing industrial chemistry using silicon is not an analog to, it's not comparable to the possible use in biochemistry based on silicon. Yeah, I think that's a reasonable sort of summary. That's actually a very interesting point they're making there that I had not considered. Yeah, because something is suitable for industry does not necessarily have any reflection on whether it's suitable for life, and the same could therefore be said of silicon. In fact, the modern copolymer industry has many examples of very diverse organosilicon polymers containing many different silicon-bearing monomers in a single or cross-linked polymeric chains. Many industrial polymeric structures are produced on a very large scale. For example, popular silicones are produced in an impressive amount of 2 million metric tons per year. Silicon is known to form stable polysilane polymers with a silicon-silicon scaffolding containing as many as 500 consecutive silicon-silicon bonds. Shorter chiral oligosilanes with up to 26 consecutive silicon-silicon bonds were also synthesized. Such oligosilanes are capable of supporting many different side chain groups of variable chemical functionality, including carboxylic acid groups that are soluble in water and can self-aggregate into amphiphilic vesicles and micelle-like structures, or alkyl side chains that are soluble in nonpolar solvents. Note that carbon often plays the role of a heteroatom in polymers that are scaffolded by silicon. So technically I was wrong earlier, and there is quite a degree of chemistry that involves carbon attached to silicon scaffolds, which is good to know. Although that's actually that is actually fascinating. The idea of amphiphilic vesicles on micelles is, as I recall, somewhat similar to how soap bubbles form, and somewhat similar to how potentially very early cell membranes could form. I think I got that right. And that is a vital part of potentially early life on Earth. I'm sure if somebody's reading this and understands it, they'll probably correct me, but who knows? Maybe that will give me an opportunity to go through and correct myself. There is, therefore, little doubt that the true chemical diversity of silicon-bearing polymers is sufficient to build a complex scaffolding of biochemicals, analogous in their biological functionality to proteins, nucleic acids, or carbohydrates in Earth's biochemistry. The capability of a scaffolding element to build diverse molecules, especially polymeric structures, is likely one of the universal requirements for life, no matter its underlying chemical composition. Silicon clearly meets that requirement. Furthermore, silicon chemistry can also lead to the formation of molecular barriers necessary to achieve compartmentalization, another likely universal requirement of life. For example, formation of complex macromolecular assemblies that can potentially serve as molecular barriers, akin to lipid bilayers in Earth's carbon biochemistry, is also known. Examples of such large flexible systems include sheets, tubes, strings, and many other shapes that can be formed by various derivatives of silane polyols. Even on Earth, life recognizes a unique advantage of silicon as a useful structural element. They're actually talking about things like skeletons in sponges, I think. But I'm glad that my understanding seems to be more or less correct. I'm actually finding this quite fascinating. The substitution of silicon for carbon in the context of the silicon-carbon bond has been sufficient. Let me start that again. The substitution of silicon for carbon in the context of the silicon-carbon bond has been successfully demonstrated for a series of pharmaceutically and biologically important compounds, including amino acids. In some cases, the silicon-containing group is incorporated as a side chain substituent in peptide-like backbone-containing molecules, for example in silane diols. Only very recently the silicon atom has been incorporated at the central alpha position of an amino acid in a peptide chain forming short silicon-based peptides such as, oh, 7. Where's 7? This one. Yeah. Sorry. Don't know what that is. Synthesis of alpha-silyl peptides further exemplifies the potential for silicon as a heteroatom in the context of aqueous biochemistry. We conclude that silicon chemistry can provide equivalent density of function to carbon chemistry from the point of view of theoretical as well as synthetic functional chemical space. Science fiction writers, start taking notes. Actually, that's a silly comment because science fiction writers that would go into this stuff are far more knowledgeable about it than I am. Thermodynamic aspects of formation of silicon compounds. We now address the thermodynamics of formation of silicon chemicals, providing a new analysis of energies of formation of silicon chemicals. While thermodynamics is never an absolute barrier to life, chemicals that are energetically costly to make might be underrepresented in metabolism if less energetically costly functional equivalents are available. In this section, we discuss whether there is a thermodynamic barrier to the formation of a diverse space of silicon-containing molecules, and explore if basic thermodynamics could be the reason for the improbability of silicon-based biochemistry. All compounds containing silicon bonded to atoms of similar electronegativity, silicon and phosphorus, require substantially more energy than to make, all compounds containing silicon bonded to atoms of similar electronegativity require substantially more energy to make than equivalent carbon compounds. This is actually a very important point. However, silicon bonded to atoms of greater electronegativity, including carbon, is relatively more thermodynamically favorable. Negative delta G formation from SiO2. Note that SiF4 is actually more thermodynamically stable than CF4. This observation is consistent with the fact that silicon tetrafluoride is stable and produces a trace gas by volcanoes on Earth. Our thermodynamic calculations show that the energies of formation of silicon-containing compounds are generally much higher and therefore less favorable than their carbon counterparts. Such a high thermodynamic cost of the synthesis of silicon compounds could contribute to the scarcity of silicon in biochemistry. It is not, however, an absolute limitation. So essentially, if you have the potential of carbon biochemistry and silicon biochemistry, the ease of formation of carbon biochemistry would be favored over silicon biochemistry because it's easier. Potential for silicon biochemistry in different solvents. A solvent provides the immediate chemical requirement for life. In this section, we discuss the general requirements for silicon biochemistry through the lens of the solvent by assessing the degree to which several of the cosmically abundant liquids can support complex silicon chemistry. In this paper, we focus on the examples of the most plausible and cosmically abundant solvents. We note, however, that some speculations have suggested the possibility of liquid rock as a solvent for life. Wow, I must admit I had never heard of that one. That is completely new to me. Feinberg and Shapiro postulate a planet Thermia with a surface temperature above the melting point of rock and silicate-based life swimming in it. Although such a liquid would be composed of silicates, it is not a plausible host for silicon using biochemistry. Covalent bonds in silicate rocks are SiO bonds, the strongest bonds silicon forms. All the covalent bonds in solid rock are mobilized on melting, becoming no more stable than the hydrogen bonds in liquid water. Of necessity, no complex silicon-based compounds could be stable in an environment where the silicon-oxygen bonds are being broken on a millisecond timescale by heat. Although we note that planet Corot 7b could be a real universe model for Feinberg's and Shapiro's planet Thermia. Throughout, when we discuss the abundance of rarity of silicon in biochemicals, we refer to the number of chemical structures containing silicon, not the total mass of silicon compounds in the biosphere. This is also an important point. On Earth, carbon-based biochemistry can only exist below certain temperatures. For example, that's why you don't find complex life where you might find, what do you call them? Heat-loving organisms, thermophiles. Any higher temperature and basically the biochemistry falls apart. So what you're going to get is the same problem with silicon-based life, which is why the hypothetical planet Thermia seems to be regarded here as not being particularly plausible because it would just break down. Silicon biochemistry in water. Only a tiny fraction of the theoretical chemical space of silicon chemistry can be stable in water. In fact, some of the commonly held views about the low diversity of silicon chemistry come directly from the instability of silicon chemistry in water. Silicon chemistry in water also requires substantially more energy to access than equivalent carbon chemistry. For all of the above reasons, we argue in this subsection that silicon is unlikely to be a scaffold element or a common heteroatom element in water. Silicon may be a rare heteroatom found in a small number of chemicals where the stability and/or thermodynamic barriers are sufficiently minor. The observation that the biochemistry of silicon in terrestrial organisms is extremely chemically limited is consistent with the limitations of silicon chemistry in water. All biological silicon-containing structures are derivatives of only one molecule, silicic acid, H4SiO4, and its dehydration product, silica. In all of Earth's life, the silicon atom is bonded exclusively to oxygen, forming an SiO single bond. No naturally occurring life forms synthesize bonds between silicon and any other atom. Which is actually a very good argument. And remember, the SiO is the strongest bond that silicon can form. Oops. I hope I'm pronouncing silicic acid correctly. We now turn to discuss two scenarios in which silicon chemistry can potentially be used in water-rich environment. Silicon cannot be used as a scaffold or major heteroatom element in water. Biochemistry based purely on silicon-silicon scaffolding is almost certainly impossible in water. Many silicon-silicon compounds hydrolyze almost instantaneously in water. The hydrolytic instability of the majority of silicon compounds is likely an unavoidable barrier to exclusive silicon-silicon scaffolding of life in aqueous environments. Similarly, silicon as a major scaffold bonded to hydrogen, nitrogen, sulfur, or phosphorus atoms is implausible for its hydrolytic instability. It is, however, possible to envision a scenario in which both carbon and silicon together play a role in scaffolding of biochemistry. The possible scaffolding scenarios for such silicon-carbon hybrid biochemistry could include silanolate, silicon-oxygen-carbon functional groups, not unlike the proposed crosslinks in plant cell wall or vertebrate extracellular matrix, although these are also hydrolytically labile. A hybrid backbone could also be built of silicon-carbon single bonds. The silicon-carbon single bond is a strong, water and otherwise solvent-stable covalent bond that in principle could be utilized in biochemistry as a scaffolding. Such use of silicon would be analogous to the role nitrogen plays in the backbone of proteins or that of phosphorus and oxygen play in the backbone of nucleic acids. However, including silicon as a major scaffolding element would have to give a very significant evolutionary advantage that would offset the tremendous energetic cost of mobilizing large amounts of silicon. Thinking for a second here. There was a comment in the back of my head. Yes, essentially, in terms of the chemistry and natural selection within chemistry, which is necessary for life to form, it is more likely that carbon-carbon would be chosen because it's easier and works than carbon-silicon, which is much harder. So if you've got carbon and silicon around, carbon-carbon is therefore more likely than carbon-silicon. I hope I've interpreted that correctly. At least that's my understanding. However, I won't speculate. I've noticed sometimes where I speculate, they then talk about it in pretty much the next paragraph. In a water-rich environment on a typical rocky planet where the carbon-oxygen ratio is heavily skewed towards oxygen, the main form of silicon will be sequestered in highly unreactive and insoluble silica-rich rocks. See Appendix B for the discussion of rare exceptions from this rule. The excess cosmic abundance of elemental oxygen, as compared to other elements that silicon could be stably bonded with, ensures that the great majority of the available silicon is almost exclusively bonded to oxygen. Similarly, a very high affinity of oxygen to silicon makes it unlikely that bonds between silicon and other elements, like silicon-silicon or silicon-carbon, would be anything but a rare oddity in environments where oxygen is plentiful. It is therefore very likely that silicon chemistry on the planetary bodies in the galaxy is dominated by the chemistry of silicon and oxygen in the silica rocks. Also a very valuable point. What they could be leading to here would be speculation on silicon biochemistry in an oxygen-free or low-oxygen environment. In other words, I'm not necessarily thinking we're talking about atmospheric oxygen, just the presence of oxygen. It does make me wonder. Hang on, where were we? Ah, right. Okay. Mental note. I'm at the word utilization. I am wondering. A breakthrough experiment in the formation of organic compounds on Earth was the Miller-Urey experiment, which basically, while it's not directly analogous to early Earth atmosphere, basically took a proposed atmosphere for Earth and ran an electrical spark through it. And in the process, they created, I think it's something like 20 different amino acids, some of which, or if not all of which, were necessary for life on Earth. I am now wondering if anybody's tried to do something similar with silicon. Now, the thing that occurs to me, thinking about that for even half a second, is that I think the Miller-Urey experiment used water, and I can't remember the other compounds off the top of my head. I'd have to look it up. But they were gaseous. So you'd have to therefore try it with some other solvent other than water, although water would be an interesting experiment. I'm not sure how you'd provide silicon into that. You wouldn't be able to have oxygen. Okay, suddenly that's an experiment I'd love to look up and see whether it has been done. Because if you used sulfuric acid as the solvent and then you had other gases, how would you provide silicon into that mixture? Not entirely sure. I'm going to have to look that up. Now I'm curious. And I hope I'm not diverging away too much, and I hope my speculation isn't completely false. Utilization of silicon for building a rich and chemically diverse biochemistry in water necessitates prior breaking of the silicon-oxygen bond, a feat that as of yet life on Earth appears to be incapable of doing. The incredible stability and strength of the silicon-oxygen bond makes hybrid silicon-carbon scaffolding using silicon as a major heteroatom element tremendously energetically costly and therefore very unlikely. It does not mean, however, that such silicon-carbon scaffolds for complex biochemistry are completely impossible. In environments on planets which have carbon-oxygen ratios favoring carbon over oxygen, or with much less overall oxygen content, the hypothetical carbon planets, the main building blocks for silicon-carbon hybrid biochemistry might be much more readily available. It is important to stress, however, that such environments might be very rare. And that is actually pretty much what I was saying, I think. And no, I have read this, but I don't remember it. I'm not reading from a script. I am making up my comments as I go along. If I were reading from a script, I would not be streaming this. Where's the fun in reading from a script? Well, I am technically reading from a script, aren't I? My comments are not scripted. Silicon can be used as a rare heteroatom element in water. We now present several examples of how silicon could in principle be used as a rare heteroatom in water-rich terrestrial biochemistry. The fact that life on Earth does not use silicon in any other capacity than silicic acid and silica is not in itself an evidence for an inherent limitation of life's biochemical machinery. For example, life cannot make silicon-chlorine bonds in water. Similarly, silicon-hydrogen bonds hydrolyze to SiOH in a matter of a few hours under mammalian physiological conditions, which is relatively warm. But silicon-carbon bonds that are stable in water could in principle be used by life. No natural enzyme system can break silicon-oxygen bonds and synthesize silicon-chlorine bonds. I wonder if that should say no known natural enzyme system. Oh, they're talking about on Earth, aren't they? Naturally occurring terrestrial enzymes possess silicon-containing drugs and synthetic molecules by the carbon. How do you pronounce that? Moieties? With silicon-containing functional groups left intact or readily hydrolyzed. However, the possibility for silicon's incorporation as a rare heteroatom in organic molecules by water-based life appears much more likely than previously thought, thanks to a series of elegant experiments in directed evolution by Francis Arnold's laboratory. The experiments suggest that at least to some capacity, life is capable of evolving means to create silicon-carbon bonds previously not known to biology. Ooh, that is interesting. A chiral silicon-carbon bond is catalyzed by an artificially involved variant, and I have no idea what that is. Rhodothermus marinus cytochrome. I would have to look that. Oh, okay. I'm going to look that up. What is that? This is why I have search engines up. Rhodothermus marinus. Oh! A thermohalophilic bacterium. There's very little information about it. It's a species of bacteria. Huh. Fascinating. Wow, that actually is fascinating. They've managed to get an artificially involved variant of a bacterium to catalyze a chiral silicon-carbon bond. Huh. That is absolutely fascinating. I'm going to have to check up on that. Yes, in fact, they have the footnotes, so I will at some point check up on that. However, the formation of the silicon-carbon bond happens in contrived conditions, in a thermodynamically favorable conversion of the silicon-hydrogen bond in phenyl dimethylsilane substrate to an additional fourth silicon-carbon bond. Such experiments show that terrestrial biochemistry could create silicon-carbon bonds, but not how it could reduce silica to a silane as the feedstock for such a reaction. See? Perfectly comprehensible. Actually, it is. But that is absolutely fascinating. I did not know that that had been achieved. I'm wondering how I'm going to share this with my son if he's interested. Oh, but he's the one doing chemistry. Perhaps I'll just shoot him the paper. He's more likely to be able to understand it than I am. His chemistry knowledge is much more recent than mine. The concept that terrestrial life could use silicon bonded to carbon as a rare heteroatom is supported by the example of boron in biochemistry. Boron is present in Earth's crust as borate, which, like silicate, requires substantial energy to reduce. Boron, like silicon, is used widely by life as an oxyacid. Compounds containing boron-carbon and boron-nitrogen bonds, like silicon compounds, are known to organic chemists and used in pharmacology. So there is clear evidence that organoboron compounds have useful biological functions. However, unlike the case of silicon, there is a reported example of boron as a heteroatom in a natural compound containing a boron-carbon bond, suggesting that there is an evolutionary benefit to breaking the difficult boron-oxygen for inclusion of boron in biochemicals. The example of a phenyl boronic acid, a natural boron-carbon bond containing compound isolated from cranberry fruit, shows that life is capable of overcoming the very high energetic cost of breaking and chemical transformation of the very stable boron-oxygen bonds if there is a useful function for such chemistry that cannot be achieved through other means. It is not known what that advantage is. Oh, that is very interesting. They know it's there, but they don't know what it's used for. At least they didn't 4 years ago when this was written. It is very much possible that similarly to organoboron, some small number of organosilicon natural products with silicon heteroatoms await discovery. Therefore, looking for analogous natural products containing a silicon-carbon bond is not without merit, especially since, as we discussed below, organosilicon chemicals could provide life with a unique and useful biological function. Such an evolutionary advantage might be enough to offset the energetic costs of breaking the very stable silicon-oxygen bonds. What might that selective advantage be? Clearly, it must derive from the unique chemistry of silicon, and one such chemistry is the unique chemical functionality of silanols, silane diols, and silatriols, of which they have examples below. Silanols, silane diols, and silatriols are silicon-containing analogues of alcohols that are characterized by unusual solubility properties, often being similarly soluble both in water and other solvents like hexane. Such solubility behavior is likely the result of the formation of strong hydrogen-bonded molecular complexes in solution. Such enhanced hydrogen bonding abilities and increased acidity of silanols relative to carbon analogues have potentially useful biological applications that their carbon analogues cannot provide. For example, silane diols are present almost exclusively as the germinal diol tautomer over I completely don't understand that at all. I'm going to have to reread that. Such enhanced hydrogen bonding abilities and increased acidity of silanols relative to carbon analogues have potentially useful biological applications that their carbon analogues cannot provide. For example, silane diols are present almost exclusively as the geminal diol tautomer over silanane. Silane diols mimic the geminal diol form of carbonyl as a transition state analog in the catalytic cycle of proteases. They are therefore considered potate protease inhibitors. This characteristic of silicon organic chemistry could potentially be explored for a useful biological function by water-based terrestrial life. And I apologize, I would have to reread that several times to get it fluid, because for a second, for me, that was not dissimilar to reading legalese in a privacy agreement. Whoops. In conclusion, the use of silicon in the capacity of a rare heteroatom for water-based biochemistry can, in principle, provide life with unique biological functionality of silicon chemistry that cannot be provided by other heteroatoms. In theory, this advantage might counterbalance the significant energetic expense to an organism to mobilize silicon from inorganic silica. The water stability of silicon-carbon and silicon-oxygen bonds makes them potentially attractive as carriers of useful biological functions and opens up the possibility for specialized utilization of silicon as a rare heteroatom. And as they said, if we happen to find biological uses for silicon other than in silica, where they've had to break, where the organisms had found it necessary to break the silicon-oxygen bond, if we find one on Earth, that would go a long way to modifying thinking about the usability of silicon as a biological function. Silicon biochemistry in non-aqueous acid-base solvents. A number of protic solvents have some chemical similarity to water and could in principle be solvents for life. However, bearing chemical similarities to water, protic solvents pose challenges for silicon biochemistry. The principal protic solvent similar to water is ammonia. Both water and ammonia are acid-base solvents that self-ionize to form a significant concentration of conjugate acid and conjugate base, H3O plus OH minus in water, NH4 plus NH2 minus in ammonia. The conjugate acid can act as an electrophile or Lewis acid, the conjugate base as a nucleophile or Lewis base. Ammonia on planetary bodies is unlikely to exist as a pure solvent for two reasons. First, ammonia vapor is easily phytolyzed to produce molecular nitrogen, a process that is effectively irreversible outside of the deep atmospheres of giant planets. A substantial planetary ammonia ocean could therefore only be maintained if the planet atmosphere and surface is protected from UV radiation. Secondly, oxygen is cosmically more abundant than nitrogen, such that any environment with condensed ammonia would also have condensed water. Because ammonia and water are fully miscible with each other, the result would be a mixed water-ammonia ocean. In any event, an ammonia solution is quite basic, and as a result very aggressive to silicon chemistry. As a strongly protonating solvent, we would expect ammonolysis, an analogous process to hydrolysis in water, to pose a serious limitation to any complex chemistry in NH3 solvent. As far as we are aware, however, silicon compound chemistry has not been studied in liquid ammonia. Other protic solvents could include H2S and HCN, but they are not cosmically abundant and not expected to be commonly present on planetary bodies. Now, there are environments in our own solar system where you have a solid surface and a liquid ocean underneath. This is very much a thing. We see this on the first two that come to mind are Europa and Ganymede. and I believe there are several other moons which also have subsurface oceans. So what we're postulating here, in principle, could be an ammonia subsurface ocean, except that if you have ammonia, as they point out, you will get water. So that has some complexities, but it would still be interesting to investigate. And cosmic abundance is important. You're not going to get a lot of life on Earth is based around some of the most chemically abundant elements. You're not going to get them in isolation. So nitrogen and hydrogen, you're not going to get them really separated from, say, oxygen. So where you will find nitrogen, you will very likely to find oxygen. It would take an astrobiologist or an astrophysicist to try and maybe come up with some environment where the oxygen is not present. That's beyond me, but still. And now we're getting to the really interesting bit. Granted, for me, this has actually all been quite fascinating. What time is it? Okay. It's nearly 10:30. I might have to go at 11-ish, in which case this will be probably split up into 2 parts. But I still intend on finishing this today. Silicon biochemistry and sulfuric acid. Sulfuric acid is considered an even more chemically aggressive solvent than water, and, as a consequence, an implausible solvent for biochemistry. Yeah, that's putting it mildly. Terrestrial biochemistry is rapidly destroyed by concentrated sulfuric acid. However, we have found, unexpectedly, that a significant fraction of silicon chemistry is stable in the harsh conditions of concentrated H2SO4, despite sulfuric acid's highly aggressive polar and chaotropic character. Below, we expand on the chemistry of silicon and sulfuric acid and assess the viability of silicon biochemistry in this unforgiving solvent. Silicon chemistry is more stable in sulfuric acid than in water. Perhaps surprisingly, a larger fraction of silicon chemical space is stable in concentrated sulfuric acid than in water. This is because much of the instability of silicon compounds in water arises from nucleophilic attack by OH- ions on the positive silicon atom, and the stability of the resulting pentacoordinate structure. In contrast, in concentrated sulfuric acid, electrophilic attack dominates, and silicon atoms, despite being electron poor in almost all compounds, are not sufficient targets of electrophilic chemistry. Such a difference in reactivity means that a range of chemical groups are stable in sulfuric acid but relatively unstable in water. For example, trifluoroalkyl groups, that's alkyl SiF3, are almost instantly hydrolyzed in water, whereas they are stable in concentrated sulfuric acid. Chlorosilanes take hours to days to hydrolyze in 100% sulfuric acid at 20 degrees centigrade, whereas in water they hydrolyze effectively instantly. Alkyl silanes are resistant to cleavage of the silicon-carbon bond under sulfuric acid conditions that would sulfonate an aromatic group. Silicon-silicon bonds are more stable in 100% sulfuric acid than silicon-carbon bonds that are themselves also stable in sulfuric acid if the carbon is aliphatic. I got that right? Aliphatic, not aromatic. Silicon OH groups can be sulfated to form sulfate esters depending on conditions. There's that word again. I'll have to ask my son how to pronounce that. Silane moieties, SiH bonds, are stable to reaction with sulfuric acid at room temperature in some contexts. In others, where ring strain is present, for example silocyclopentane, they are hydrolyzed. Note that silicon-hydrogen groups are stable in pure water, but the slightest trace of alkali compounds, including the presence of ordinary glass, catalyzes their rapid hydrolysis. There is no data available on the stability of silicon-sulfur and silicon-nitrogen bonds in sulfuric acid. There are very few exceptions to the above. Silicon chemicals that are more stable in water than in sulfuric acid. Oh, I read that badly. There are very few exceptions to the above. Silicon chemicals that are more stable in water than in sulfuric acid. One notable example is that silicon phenyl bonds are readily broken in sulfuric acid but not in water. In addition, low molecular weight silicones are generally more readily rearranged into silanols or sulfate esters in sulfuric acid than water. And this is almost certainly going to be having to be broken down into two parts, which I will endeavour to complete. I'm trying to think. I'm going to finish this current section and then continue either this afternoon, and I might do it tomorrow. Yeah, because this is... for some reason I thought this would be quicker. I'm not quite sure why, but yeah, I'm going to finish this section and then call a halt, upload it, and then part 2 will follow on. Possible and true, my ability to pronounce words is now degrading, like silicon bonds in water. I'm being hydrolyzed. Oh, talking of hydrolysis. No, this isn't hydrolysis. The fact that a larger number of silicon functional groups appear to be stable in concentrated sulfuric acid than in water opens the possibility for hypothetical life in sulfuric acid to use silicon to a considerable extent. We therefore turn to specific examples of chemical functionalities of silicon chemistry in sulfuric acid. The first functionality comes from the very stable hydrogen bonds that silicon compounds can form in general. For example, silicon OH and silicon fluorine bonds are highly polarized and would be expected to form extremely strong hydrogen bond donors and acceptors respectively. The silicon-hydrogen bond strength could be valuable to overcome the chaotropic effects of sulfuric acid in forming stable macromolecular structures. The hydrogen bond energies between silicon fluorine and HX are not known, but the energy of the similar very stable hydrogen fluorine hydrogen OH dimer hydrogen bond is about 45. I can say that can't be minus 45. Is about 45 kilojoules per mole, compared to the H bonds involving SiF are expected to be even more stable. Ooh, sorry, missed a bit. Compared to the HOHH-OH dimer of 21 kilojoules per mole. With silicon being slightly more electropositive than hydrogen, H bonds involving silicon fluorine are expected to be even more stable than hydrogen fluorine ones. Silanes, silicon molecules containing silicon-silicon bonds, can exclusively provide another potentially useful biological functionality for hypothetical sulfuric acid-based life. The Si-Si chains, many of which are known to be stable in concentrated sulfuric acid, have a degree of... Okay, I'm going to have to go back to my... That's not alpha, is it? Oh. Greek alphabet in order, and... Sorry, I need to check this. Where was it? I want to get this right. Delta. Is that delta? Oh no, it's sigma. All right. And it's sigma, apparently. My son would not have made this mistake. Well, he wouldn't have probably had to look it up. Oh, where was I? Oh, I'll just start from here. Silanes, silicon molecules containing silicon-silicon bonds, can exclusively provide another potentially useful biological functionality for hypothetical sulfuric acid-based life. The silicon-silicon chains, many of which are known to be stable in concentrated sulfuric acid, have a degree of sigma orbital overlap that allows electron conduction down the scaffold of the molecule. Such electron conduction is analogous to conjugated alkene systems in Earth life's biochemistry. Conjugated alkenes, such as isoprene, are very rapidly attacked in concentrated H2SO4, and so in principle long-chain silanes in sulfuric acid could substitute for biochemical functions carried out by conjugated dienes in terrestrial chemistry. I hope you're making notes. There will be a test later. We also note that some silicon-containing polymers are highly resistant to sulfuric acid. For example, polymers where silicon and carbon atoms alternate in the backbone, rather than the silicon-oxygen alternation of silicones, are stable to 98% H2SO4 at 90 degrees centigrade. Such unique silicon chemistry might also provide necessarily biological functionality that is otherwise different to attain in sulfuric acid through exclusively carbon-based chemistry. We emphasize that these examples of potential biological uses of silicon chemistry are speculations, not predictions. We use them here solely to illustrate that silicon has specific potential advantages as a heteroatom for compounds in a sulfuric acid solvent, advantages that either do not apply or apply less in water. Adding silicon to the repertoire of structures available in sulfuric acid has a greater positive impact on the available structural and functional chemical diversity than in water. This greater scope of stable silicon functional groups could result in greater evolutionary advantage for sulfuric acid-based life as compared to Earth's water-based life to use silicon chemistry. Not only is the size of available silicon chemical space in sulfuric acid greater than that in water, but the overrepresentation of stable silicon functional groups could offset the smaller number of carbon-based functional groups that are stable in the ingressive conditions of concentrated sulfuric acid. Therefore, the evolutionary pressure for any sulfuric acid-based life to explore silicon does not come solely from the advantages of the larger scope of available silicon chemistry, but also from the potential necessary to explore silicon chemical space in sulfuric acid to perform biological functions. And now we're getting really interesting. As if I haven't found this fascinating enough as it is. Planetary environments with sulfuric acid. Sulfuric acid has been suggested to be an abundant solvent on the surface of planets. However, unlike other speculated high-temperature solvents, such as HCN and NH3, there is a precedent in the solar system for the planetary scale of existence of liquid with concentrated sulfuric acid, and that is the Venusian clouds. Of course. Yes, that makes perfect sense. Venus has a separate cloud layer, a region spanning from 48 to 60 kilometers altitude with temperatures less than 100 degrees centigrade and pressures less than 2 bar, believed to be composed of liquid sulfuric acid droplets. A permanent Venusian aerial biosphere has been the topic of scientific speculation for many decades. It is unknown what biochemistry could exist in such a highly reactive and aggressive protic solvent as sulfuric acid, but as our discussion above indicates, a biochemistry that makes wider use of silicon is a possibility. Silicon biochemistry in cold aprotic solvents. Silicon chemistry, really any chemistry, is much more stable in aprotic solvents than in protic solvents. Aprotic solvents are non-ionizing solvents, which, unlike protic solvents like water or ammonia, do not contain labile H+. In planetary terms, common aprotic solvents such as methane, ethane, and ethane and nitrogen that not only form liquid phases at very low temperatures are commonly called cryosolvents. Here we use the term cryosolvent, short for cryogenic solvent, a solvent that is liquid at temperatures below minus 100 degrees centigrade for cold aprotic solvents. Ooh, I wonder if they're going to mention Titan. Planetary environments with cryosolvents. Surface seas of aprotic cryosolvents might be a common occurrence on planets. In fact, aprotic cryosolvents like methane, ethane, C2H6, or liquid nitrogen may be the most abundant liquids on planetary surfaces, based on an exhaustive analysis of the propensity of stable surface oceans composed of liquids different than water. N2 itself is a very common chemical on the cosmic scale, with abundances rivaling that of water. Surface non-protonating solvents like liquid nitrogen oceans could be especially common on planets or moons orbiting M-dwarf stars. The very low melting, minus 210 degrees centigrade, and boiling points, minus 196 degrees centigrade, of nitrogen necessitate that planets and moons hosting liquid N2 oceans have to receive far less incident stellar energy than planets hosting water oceans. Ooh, now the first thing that occurs to me about that is that they would be receiving much less energy from their star, which would slow down potentially chemical reactions. One of the things that we have going for us here on Earth is that we are in a, what they call the Goldilocks zone. We get a lot of energy from the sun, and however this forms, it's going to need some form of energy, either from the sun or from the Earth or Moon's core, or from orbital dynamics such as Io experiences. The corresponding large planet-star separation, for example, greater than 1 AU for an M5 star, could mitigate the detrimental effects of high stellar activity of M-dwarf stars. Planets orbiting close to the stars may be subjected to the catastrophic loss of an atmosphere from stellar flares. Such advantages could result in stable, clement conditions that could potentially allow for liquid N2 oceans to persist on a planetary surface for billions of years, despite the relatively narrow temperature range for liquid N2. Such conditions could also exist in our own solar system, on Neptune's moon Triton, which orbits an N2 habitable zone. Did I say Triton or Titan? No, Triton is Neptune. I was wondering if they're going to mention Titan. The low temperatures of aprotic cryosolvent seas pose at least two serious limitations on solvents for life, regardless of if life is silicon or alternative carbon-based. The first problem is the low rate of any chemistry at such low temperatures. The second problem stems from the low solubility of molecules at cryogenic temperatures. Of these two temperatures, the first, that is, slow rates of chemical reactions, is easier to overcome. They haven't mentioned Titan. And I'm wondering if you could have a planet or moon with a Europa-like environment where you have a liquid nitrogen ocean underneath a solid crust. But that would require frozen nitrogen or... Okay, getting beyond me. I am engaging in wild speculation which the chemists out there would probably wince at. What time is it? Low chemical reactivity in cryosolvents. Slow reaction rates could be prohibitive for the formation of or reactivity between complex molecules. Chemical reactions occurring in cryosolvents would proceed very slowly, much more slowly than in Earth's surface environment. The speed of chemical reactions generally drops by a factor of 2 to 3 for every 10 degrees centigrade temperature decrease. This drop of chemical reaction rate, however, is not an absolute limitation. It could actually be an advantage specific to silicon chemistry. The key factor is the formation of complex chemicals at any temperature, is the selection of chemical reactions that are specifically tailored to a given temperature range. Many silicon chemicals that are too reactive at Earth's surface temperatures may have chemical reactivities just right at the temperature ranges of cryosolvents, including very low temperatures of liquid N2. Silicon can do very fast chemical reactions at extremely low temperatures of liquid oxygen, as exemplified by experiments on the reactivity of amorphous silicon and oxygen. Hang on. Did I just do that? That's slightly confusing. Hang on a second. Okay, nope. Specifically, two features of silicon chemistry support the notion that the reactivity of complex silicon chemistry could be uniquely suited for cryosolvent temperatures. First, the increased reactivity of silicon, a disadvantage in water, could be an advantage in cryosolvents. Silicon is much more electropositive than carbon. Most silicon bonds with nonmetals are more polarized than the equivalent carbon bonds. As a result, such bonds are more liable to electrophilic and nucleophilic attack, allowing chemistry using weaker nucleophiles or electrophiles. Such reactivity is predominant in solvents like water and ammonia. Such differences in reactivity are important because strong nucleophiles or electrophiles are themselves likely to be polarized and hence insoluble in cryosolvents. Additionally, common Si-X bonds are generally weaker than the equivalent carbon X bonds, and as such require less thermal energy to break for any given reaction mechanism. Again, weaker bonds might be considered an advantage over classical carbon chemistry in very low temperature environments. One thing that occurs to me though there is, if that is the case, why have we not found more complex silicon chemistry on asteroids, where we do find complex carbon chemistry? The inherently greater reactivity of organosilicon-based chemicals could also be an advantage through enabling greater control and regulation of silicon-based biochemical processes. For example, chemical reactions involved in the formation and breakage of hydrogen bonds are much slower at cryo temperatures, which could allow for more complex regulation of their formation by catalysts. The much stronger nature of hydrogen bonds in cryosolvents could stabilize molecules to a much greater degree than in liquid water at Earth's surface temperatures. While, sometimes, such stabilization effects might be viewed as a detriment, for example, much stronger silicon OH-H bonding, they could be beneficial for easy catalytic control of reactivity and stabilization of genetic polymer molecules of hypothetical silicon-based life forms. Secondly, in non-polar cryosolvents, many silicon-bearing functional groups that are completely unstable in water, including exotic unsaturated silanes, are stable and could in principle be utilized for useful biological function. Such higher structural and functional diversity of silicon chemistry in cryosolvents could make utilization of silicon chemistry much more attractive for life and could potentially offset the high energy requirements needed for cleavage of the SiO bond and the mobilization of silicon from silica rocks. For example, functional groups containing multiple bonds between silicon atoms are well known, but so far are only known to be stable in sterically constrained compounds, that is, compounds where other silicon valences are occupied by very bulky groups, and in the absence of water, ammonia, and a range of other groups like carbonyls and alkynes. In colder environments, such systems, though still reactive, are stable enough that their reactivity is much easier to regulate and control, and hence be much more useful. Thus, the generally lower reactivity of chemicals at cryogenic temperatures is likely not a major barrier for silicon chemistry in cryosolvents. Excuse me. How much further to go before I... Okay. I am going to have to call it a stop there because, hang on, let me check my phone. Yeah, I believe I have an appointment in shortly that I have to get to. Hoped that I would be able to get through all of this, but yeah, the synthesis and conclusions is fairly extensive. Then we've got the biochemistry of life on Earth, and yes, we still have quite a bit to go, and we're just over halfway through. So, if you're watching this on YouTube, this will be part one. Part two will appear when I can get it done. And if you're watching this on a live stream, part two will be, I want to say tomorrow, but actually I still want to do my Minecraft base stream tomorrow. So now we're looking at Thursday. So hopefully that wasn't too boring. I personally and fairly obviously found it quite fascinating. And in the interim, between now and the next stream, or now and the next time you continue watching this feature, I hope you all have a good day/week, and I will see you soon.